Hello everybody, welcome here to another video by JFB, and in this video we are finally gonna build a logic circuit. What is a logic circuit? Well, a logic circuit, you can actually get it from its definition, is a circuit which has simply implements logic, just like a logic gate, a gate which just implements some logic. That's a logic circuit. And an example of a logic circuit is one actually which is very common in computer science, and it's called the half adder. What is a half adder? You can just think of it as a half adder is simply a circuit that can add up numbers. That's what it is. So a half adder adds up numbers to give you a sum. That's all there is to it. So a half adder in this case will only add up numbers in binary form, since we're just using logic gates to implement this thing. And remember, logic gates only take in binary numbers and all those things. All the half adder is going to do is going to add those binary numbers. Now, in the previous videos where I explained on binary numbers, if you didn't watch them, I recommend that you watch them so that you can understand what actually I'm doing here. I explained how binary numbers are represented in computers and all that thing, but I never even actually taught you how binary numbers can be added. So when adding binary numbers, it's similar to how when we add denary numbers. All you need to do is maintain the numbers, that they don't go into another number system. So for example, when you add 21 plus 22, the result should always be in the denary system, and this is just 43. If you can see, the sum of this is also just in the denary system. Same to binary numbers. When you add binary numbers like 10111 plus 1111, the result shouldn't come out something like 20222. The result needs to come out as a binary number. So it needs to come out something like a 100111, something like that. That's the core principle of how binary numbers are added. Now, to build this half adder, we're gonna use a little bit of logic and some logic gates in order for it to work actually. So let me explain on how binary numbers are added. The first example we're gonna start with is the simplest: 0 plus 0. And 0 plus 0 in any number system is always 0. The next example is gonna be 1 plus 0. 1 plus 0 is 1. Well, 1 plus 0 also in the denary system is 1, and in the binary system it's also 1. Now the other example we're gonna look at is gonna be 0 plus 1. Well, this is just the same type of computation because I've just flipped, but you see the importance of why I did 0 plus 1. The answer here is just another 1. The final example we're gonna look at for the half adder is gonna be 1 plus 1. Well, this one is a little bit tricky. 1 plus 1 in the denary system is 2, but remember, there's no 2 in the binary system, so we need to find out a way we can actually convert this 2 back into its binary form. And it's quite easy. It's just like how you take the remainder in the denary system. Here's an example. I said, if you have 9 plus 9, 9 plus 9 is 18, but that 18 in maybe hexadecimal can just be represented as F2 or something like that. That's 18 in hexadecimal. So the denary system has a system whereby this 9 plus 9 can be taken back into its denary form. So 9 plus 9 is where you get an 18, but you don't write that 18 complete. You write an 8, then you write the remainder of 1. Which 1 adds with a 0, which is here. Just imagine there's imaginary zeros there. So 1 plus 0, which gives us a 1. And your answer is finally an 18. What about for 1 plus 1? Well, it's practically the same. 1 plus 1 is 2. We're not going to write that 2. We're going to write a 0 this time. A 0 and a remainder of 1. 1 plus the zeros which are imaginary here, and it's 1 0. And if you remember, 1 0 is just 2 in the binary system. Our half adder will only use 2 logic gates, and those logic gates, well, let me actually, before I state those logic gates, let's try to build a half adder right here on the whiteboard. Remember, we're only adding up to 2, so we have cases where we're gonna have 0 plus 0, which is equal to 0, 1 plus 0, which is equal to 1, 0 plus 1, which is equal to 1, and 1 plus 1, which will be equal to 1, 0. Now, in order for you to understand these logic gates, always try to drive out the scenarios all the scenarios are going to have in the binary form. Then think of a logic gate which suits the output. These equations or these expressions we're seeing here, there's actually a logic gate which suits this output. So when trying to build a half adder or any other type of logic circuit, try to map out all the scenarios. Just try a brief map out. So we have 0 plus 0, 1 plus 0, 0 plus 1 and equal to 1, 1 plus 1 equal to 1, 0. And then go through each expression and ask yourself which logic gates suit the type of inputs which you are given. And by the way, so we start 0 plus 0 equals 0. So what logic gate? These are the inputs. Just take any of these sides to be the inputs and these will be your outputs. So then to illustrate this further, you can just say this is your A, this is your B, C. So you're like trying to fill out a truth table or something like that. So you ask yourself which logic gates map to 0 plus 0 and gives us an output of 0. So I can think of 3 here. So we have the OR gate. The OR gate, every time it's given a 0 plus 0, it will give us a 0. Then 2, we have the AND gate. The AND gate only gives us a 1 when both are 1, but in this case we have 0, 0. And finally, the exclusive OR gate, aka XOR gate. The XOR gate, when both inputs are the same, it will always give out an output of 0. Then you ask yourself another question. Which logic gate do you think when the inputs are 1, 0 on the other side will give me a 1? Here we only have 2. The OR gate and XOR gate. What about in this scenario? We have 0 and 1. Which one will give us a 1? It's actually the OR gate and the XOR gate. Again, what we're seeing here, you can see that the OR gate and the XOR gate, they are repeating themselves on each expression. So we need to find the expression which will actually give us a different scenario. And luckily for us, we have the 1 plus 1 scenario. One logic gate, when you give it 1 plus 1, will give you 2 binary outputs. There is actually no logic gate that exists like that. So we need to think in other terms. We need to go back to this expression. 1 plus 1 was a 0, remainder a 1. This 1 is actually coming out from something else. It's coming out because it's a carry. But in the original expression, the original number which is coming out first is the 0. So we can rewrite this, and by the way, I'm just rewriting this, it's not correct. 1 plus 1 can be equal to 0. We need to think of a logic gate which will implement this type of logic here. So 1 plus 1, as we written before, it was 0, remainder 1. This 1 is coming out because of it's a carry. We actually don't need to consider it, we just need to consider this part here. So 1 plus 1 equal to 0. Now what logic gate, when its inputs are the same, will always give an output of 0? And the logic gate to that answer is the XOR gate. So the XOR gate has come out on every expression. So this shows that the XOR gate will be used in the half adder. It's one of the gates which will be used in the half adders. But now we need to ask ourselves, what about this one? What logic gate can give me a 1 when both of its inputs are 1? So we have 1 plus 1. What logic gate do you think will give us an output of 1 again? Well, I can think of 2. Here, it can either be the OR gate or the AND gate. Now we need to differentiate these two. Why should we pick the OR gate instead of the AND gate, or why should we pick the AND gate instead of the OR gate? You need to think more deeply here. If we pick the OR gate will kind of have a problem. The OR gate can give us a 1 in any case when we just have a 1 or a 0. But the AND gate is firm on something. It will only give a 1 when both of its inputs are the same. And we only need that 1 when both of A and B are the same. The OR gate will bring about ambiguity, and it will be quite confusing. Whilst the AND gate is straightforward. When both of the inputs are the same, it will give you a 1. Now, in the next video, I know I've extended this video by beyond what you expected, but in the next video, we'll actually implement the half adder circuit using the same website logic.ly to build a half adder.